I guess this is the procedure that you pull it down and then you push it up. Okay, so I am going to talk about approach to equilibrium. And the connection with increasing entropy. And so what kind of entropy? That is already a question mark. What the heck is equilibrium? So these are well-known concepts, but probably there are 20 definitions for each. So I will talk about probably a brand new definition, what I call geometric. And of course, equilibrium shows up everywhere. It is a basic term in thermodynamics and in whole physics and in biology and everywhere. What I am going to study is the time evolution of large point systems in motion. So let's start with and how that system approaches equilibrium. What does equilibrium means, and how does entropy, increasing entropy, show up and kind of turns out to be a manifestation of this convergence to equilibrium. So what is the model? The model is a very simple model, that we have a huge number of particles. I just represent them as points, and they are inside of a box, a cube. And to have a rough idea about what is kind of a good setup here is when we have gas molecules, then n is in the range, and this is kind of a 1 cubic meter box. Then for a typical gas, it is in the range of 10 to the 26, 27, let's pick 27. And the speed of an average gas molecule is between few hundred and a couple of thousand, so let it be 1,000 meters per second. But these will be very general theorems, so you can choose n as 1,000 or 10 billion or 10 to the 10 to the 10, whatever. But this is what I consider kind of one good example where we already have surprising corollaries of the theorems. Okay, so the first question is, how quickly does a system starting from extreme of equilibrium to some kind of equilibrium? Now, what is extreme of equilibrium? Well, the most extreme of equilibrium is when they are all in one point. What I call Big Bang. Because I love the TV show, Big Bang Theory. But it is basically almost as bad if they are all in a small corner. So when it is extremely crowded, so extremely far from uniform distribution. And now, how to define equilibrium? Equilibrium is when we have uniform distribution. Actually, I will talk about two concepts of equilibrium weak and strong.
Before equilibrium, you told us where they start, but you didn't tell us their velocities, directions. What is the initial state in terms of?
Oh, okay, yeah, of course, I will talk about velocities. That is absolutely crucial. But first, I just, oh, okay, so then let's finish it. So suppose that we start from something extremely bad, like Big Bang or very crowded, and we have to give initial velocities to the particles, and then the particles just, they don't collide with each other, but they of course collide. They hit the wall and bounce back. I assume the simplest behavior, so which is called elastic collision, that the in angle equals the out angle. So what it means is every particle has this zigzag trajectory, and all what we need is the initial velocity. Now, so what about the initial velocity? Initial velocities. Now, one very natural motivation which comes from physics, if you like, is photons, the light particles. They all move in the same speed, but of course the directions are isotropic. So every direction is the same. It's uniform on the sphere. So I call it, so they are all isotropic. I guess everybody knows what it means. I looked up the dictionary and it said every direction is the same. Isotropic. So I guess the spelling is okay.
Every direction is the same. You mean in every direction there is roughly the same number of particles going in this direction?
Well, more precisely, for every particle, the direction is a uniformly distributed random variable on the unit sphere. I didn't specify the speed yet. That was just the direction. Now, for photons, the speed is the same. So I just call it the case of constant, so, you know, constant speed. The directions are uniform on this unit sphere, but the speed is constant, like photons. Now, another very natural distribution is, of course, where for the speed we have an interval. So it is not restricted to a constant speed, but the speed is varying. And for a probabilist or for a physicist, the most natural what we actually have for gas molecules in thermodynamic equilibrium is the three-dimensional Gauss distribution, normal distribution, which was discovered by Maxwell. So physicists call it the Maxwellian distribution. So what it means is that for a velocity to fall from the origin, to fall into a box, a tiny box, depends only on the magnitude of the vector. The magnitude is the Euclidean length, the simplest norm. So the density function is this three-dimensional normal. So for velocity v, the density function is e to the negative v magnitude squared over 2. Because the magnitude is fixed on the sphere, it is isotropic, And to be really precise, I have to divide by 2 pi to the, the square root 2 pi raised to the third power, so negative 3/2. So now I am very precise. This is the density function. So this is the three-dimensional normal distribution. But I just call it the Maxwellian, because every physicist calls it the Maxwellian. Since he predicted it before they could measure it, he died young, so he didn't live to learn that his prediction was correct. Now, so what does it mean about the speed? About the speed, in terms of the speed, it is a distribution. Speed, of course, just goes from 0 to infinity. And then the density function is, of course, we have, because it is constant on a sphere, and sphere is two-dimensional, it is like x squared e to the negative x squared over 2. And this is the function. And to get integral 1, we have this. So this is the speed distribution. Just now. So these are the two speed distributions. I mean, it is always isotropic what I study. I don't study anything else, so I just have to describe the speed distribution. Of course, we can have infinitely many others, so any speed distribution is fine. I just mentioned one more. So what is this? This is uniform on the unit sphere. Another one is uniform inside the unit ball, for example. Uniform in the unit ball. Okay, the velocity is uniform in the unit ball. This is unit sphere. Okay, so and of course there are infinitely many. So we can, so this is the situation. We start from an arbitrary initial configuration like Big Bang or this or whatever my enemy picks. And what I study is how quickly, and then we choose some initial velocities according to these cases, whatever you like, the photon-like, the gas-like, Maxwellian, or uniform in the unit ball, or whatever speed distribution you like. And then the question is, how quickly does this system, for example, for this range of parameters, reaches equilibrium? Now, so the next question is, what the heck is equilibrium? How would you define it? Now, so I will talk about weak and strong equilibrium. And I start with the weak one, which is easier to define. It is simply that I take an arbitrary test set. So this is the unit cube, and here is an arbitrary test set, S. And the question is, how many particles do we have in it? Now, for example, if this is the Big Bang, the initial configuration, then at the beginning we have 0 in S. But if it's like 20%, then I would equilibrium would mean that we are very close to 20%. Now, how close? Well, because actually physicists describe equilibrium as full-blown randomness. Now, which is still very vague, but at least tells us how to pick a definition for equilibrium. Now, so full-blown randomness means that the number of particles in a 20% subset is not just around 20%, but it fluctuates with the square root, typical square root fluctuation, what we learned in Introduction to Probability Theory. And not just that, on a longer time interval, maybe not very long, even just for a few seconds or minutes, we should see the Bell curve, the normal distribution, the central limit theorem. So that would be kind of randomness, that because then it will not change. You know, the normal distribution is the fixed point, the limit distribution. So then let's just stop at the weaker form of the central limit theorem, where we have a square root fluctuation. We don't want the bell-shaped curve with the bell curve to show up yet. We stop when let's say, okay, I need a notation for the number of particles. So n sub s is the number of particles in this test set. So for example, my enemy picks a very nasty but still measurable test set, then it has a volume. So I can compare the number of particles at a given time instance. But of course, we have some initial velocities and at time t. So we
And sorry, where do you expect to see the node distribution?
that is the question. That's what I want to answer.
Over some period of time, if you count the number of points in a given set, you know,
So for example,
on average it should be the measure, but it should fluctuate.
Oh, I see.
okay, so I compare it to n times the volume, because whatever nasty it is, the test set, it must have a volume. And what I want is that this is like square root n. Now this is still vague, but if you want to be really precise, then I say the difference is less than 10 times square root n. Now 10 is okay. So when does this system reaches this point? And I call it square root equilibrium. Now even here we have two very different ways to measure how the system reaches square root equilibrium. One way is just one test set, which can be arbitrarily ugly. So we fix a test set, my enemy picks a test set, and I take a typical initial velocity, according to these cases, 1, 2, 3, and so on. And how long should we wait until this will happen at the first time? What will happen after? Does the system stay there? How long does it stay there? And so on. The second question, what you can ask is, well, not just one test set, which is ugly, but the family of all nice test sets. Now, for example, all boxes and all spheres together, or all polyhedron, polyhedron. I don't know the difference between them, but you know what they are. And they have, let's say, less than 10 vertices. So all of them, and the sphere. So let me just write, so an ugly test set, this is the first case, or S, family of all boxes, tilted, and spheres, balls. So they are nice sets. But for all of them. Okay, these are two very natural and seemingly very different ways to ask a question. Maybe I start with this. So, now we are ready to formulate a theorem. Yes?
So you can't ask for all sets?
No, that is okay, then you cannot prove anything. For all sets, even for all convex sets, you cannot prove anything meaningful. Yes, there are. I will talk about that. Now, actually, for all measurable sets, the trivial counterexample is that I will study the time evolution of one system, a fixed system, which means capital N curves in the space. The volume is 0. So let's take the complement. That has measure 1. And the system should be there, but it is never there. So this kind of totally cheap arguments prevent studying two large classes. It is less trivial for all convex sets. That is tricky, yes. So, okay, now, now here comes the, okay, so how long does it take just to reach it first time, to reach this inequality? So let me repeat this setup. My enemy, Avi, he hates me because he has his reasons. So he wants to publicly humiliate me, and he picks a test set, which is nasty. He
Makes it so that it will never happen. He will win.
Yeah, sure. That is my thought. And he also picks an initial configuration, like Big Bang, or something equally, whatever he likes, and he wants to humiliate me. Let me repeat. And then what I do, I say, let's just study a typical velocity distribution according to these cases. How long does it take to reach this? 10 times square root n.
I mean, for the first time or forever?
No, just for the first time. First time. And here comes the surprise. And let's take this totally realistic setup. N is 10 to the 27. The speed is 1,000 meters per second. This is a cubic meter box. Then for the first speed distribution, which is like photons, it takes about 100 years to reach this for a typical velocity distribution, initial velocities. In the second case, it takes less than 4 milliseconds. Let me help you. A millisecond is is a 1,000 part of a second. So what it means is, in the second case, a typical particle makes 4 zigzags, or how to call them, bounces, 4 bounces, and the system is there. In that case, in the constant speed case, like photons, it takes about the square root of capital N bounces. Now, okay, so the time to reach square root equilibrium in the first case is about square root n bounces. I guess you understand what a bounce means. So is it a good word, bounce? How would you call it? Bounces. Zigs and zags. Now, you know, square root of, okay, it is 10 to the, I don't know, 10 to the 13 is the square root, which is divided by 1,000. It is 10 to the 10 seconds, which is a few hundred years. In the second case, it is square root of log n bounces. And actually, there is even a constant factor. I am not lying, which is a small constant. So if you carry out the calculations, you get 4 bounces. 4 bounces are enough, which is like 4 milliseconds. When I first got this, I kind of didn't believe it, that there is such a unbelievable difference. Now, okay, what about the third one? You know, the fundamental difference is, of course, that in the first case, the speed is concentrated to a value. I mean a constant. You can call it the Dirac delta function. In the third case, it is actually just an interval. I mean, it is concentrated on an interval. Here, it is on the whole positive real line. So the speed distributions are very different, but what would be an intuitive explanation for this enormous difference to reach square root equilibrium? And I cannot give an intuitive explanation, because mostly when we prove something, then we already know what will happen, except we cannot prove it. But here, I cannot give an intuitive explanation. Why is it so unbelievably fast for the Maxwellian, and why is it so damn slow for the constant speed? Now, you are very smart people, so after a few seconds, you will realize the following. So this is what my clever students realized after some time, that of course, if, for example, if you start from Big Bang with constant speed, then the particles remain on a sphere, right? And the sphere is just two-dimensional. Now, of course, later you take it modulo 1, and then the pieces all come together, but still you have two-dimensional pieces in a three-dimensional box, so you feel that's why. That sounds very clever. But the problem is that you get exactly the same, I mean almost the same, maybe not 100, but 50, if the initial condition, I mean the initial configuration is not Big Bang, but the initial configuration is that they are in the middle 10%. Then you don't have a sphere. Then it is already dense everywhere. So these results, okay, so I didn't tell you something what I guess you already know. This is the worst case scenario. So it takes 100 years if we start from Big Bang or close to Big Bang. And we don't have to be very close to Big Bang. It can be like all of them are in the left half. That is basically just as bad as the Big Bang, when they are all concentrated in a point, and the time is still in the range of 100 years. When they are photons, they have constant speed. And I am talking about typical direction distribution. So for every point, you choose randomly a direction by uniform distribution on the sphere. And then for the precise statement is that for 99% of the initial velocities, because of course there are totally stupid velocity distributions. I mean, it is a joke that you can have a Big Bang and then and every particle has the same velocity. Then the same cluster moves from left to right and bounces back and forth, and nothing happens. There is no convergence to anything. So of course we have to study typical initial velocities, but what is totally shocking, or at least I think it shocked everybody, so I hope I did shock you, is that the speed distribution makes such an enormous difference. So constant speed, which corresponds to photons, is very bad. And Maxwellian is very good. It is not just very good, it is unbelievably good. Now, so this is kind of the first result, and here there is nothing about entropy. That will be the next question, that what happens to the system, what the heck increases as the system reaches equilibrium. But maybe before talking to the title of my talk, I want to say more about this approach to equilibrium, because there are many natural questions what I can answer. So, thank you. That is the next question what I want to answer. For number 3, it is the fourth root of n, bounces. Now, I'm sure you say obviously, but yeah, right. So what is this? This is about, I don't know, 10 to the 6 bounces, which is 10 to the 3rd seconds, which is 3,600 seconds is an hour, so it is 20 minutes, right? Am I right? No, I am stupid. 27 is 28. The fourth root of 28 is 7. And then this is 4. And 10,000 is 3 hours. Okay, but, okay, so, okay, 1 hour. Let's have a compromise. So it takes one hour in that case. Now, you can feel that, so what makes the difference? Now, obviously, what makes a difference is the smoothness. Smooth or not. The smoothness of the speed distribution. That makes this enormous.
Can I ask you another question? Now, this is in 3 dimensions,
Yes.
but what if it's in 2 dimensions?
Yeah, very good question. The same.
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 Well, so what about 4 dimensions?
The same. So in small, okay, there is a factor of 2 difference.
But the exponents don't change.
They don't, but there is a constant factor, and that is an absolute constant factor which does change. But 2 is the same, 3 is the same, 4 is the same. Of course, 100 is not the same. because I never bothered to compute the dependence on. I just actually focus on 2 and 3 because I am a simple person. Yes.
So for each configuration, there's an ugly test set that you can that comes up from the proof. For each configuration, there is some ugly test set that you can find that shows that it doesn't converge faster than that. Or
No, actually, it is even more dramatic. This 100-year happens what? If we, actually, you can have a nice test set, actually, whatever, 1/2 volume or 1/3 volume, so kind of whatever nice set you pick, like somebody is my friend. So enemy,
Finally, you have a
friend. Yeah, I have a friend. So my enemy picked the initial configuration, which is Big Bang-like. And my good friend picked a nice test set, which is like a box.
And you will find the translate, which is bad.
No. Then the statement is that for 99% of the initial direction distributions with constant speed, it takes 100 years. So he tries to help me. He picks a very nice test set because he is my friend. And he cannot really help me. And that is another shocking fact, that if my enemy picks the test set, then it is 100 years. I am not lying.
So you will prove
I
it.
could,
What do you mean you are
I
not sure?
could, because you don't know the proof, I could mislead you. I would just say at the end, sorry, I was wrong. In mathematics, that's okay. But I think that is a damn surprising fact, that this is so bad that even it's 50% good, 50% bad. So bad initial configuration like Big Bang, but beautiful, the most beautiful test set. Of course, we have to exclude the extreme cases like the whole cube. Then, of course, it is perfect. The empty set, it is perfect. But something 50% subset. Then what? He picks a sphere. That is very nice. And it takes 100 years.
So suppose you change the definition of equilibrium to be much weaker, where you want to just have little o1, so not square root n cancellation.
Yeah, but then it's not an equilibrium.
I understand. I'm just
So I
wondering
don't
then
like that.
You don't like it.
No, that is quick. That is quick.
Yeah.
Now, actually, that is entropy, because the entropy will exactly describe how quickly this goes down from little o to the lower, to the limit, because square root fluctuation is inevitable. That is the that is the nature of randomness. So you cannot go below that. Now, that will be entropy. So I will talk about that later, but I had to start with this to emphasize the role of the initial speed distribution, which makes an enormous difference. Now, another.
I have another question.
Sure.
Suppose that we make the definition of an equilibrium at stronger, and we ask that this inequality won't hold just for test set, but for all the possible test sets simultaneously.
Yeah. Now then, for example, are you talking about this second case when, for example, all nice sets? Okay.
With
So
all sets, it's impossible. We said it if you want all sets.
So
Because concept, it's a zero measure. The trajectory is a zero measure, so they always miss.
Okay,
all nice. That is a very natural question, I think. So all nice are rotated boxes and tetrahedrons and spheres. all together. I mean all of them. That is a family. So I want all of them to have this upper bound. Then it is the same. It is the same because the reason is that, you know, it sounds fancy that there are very relatively few nice sets. I mean, you can describe them with, for example, the vertices. Only four vertices, 3 vertices. For a circle, the center and the radius. Just 2, like 2 vertices. So
you take a unit bound.
So it means that is a very narrow family, and the proof reflects that. That's why it is almost the same as 1. But in some sense, the ugliness of the test set doesn't matter. That is a very shocking part in this business, which is again counterintuitive. Now, okay, what would be? So they are basically the same. The two questions, the waiting time is the same. I think that is very surprising. Now, so.
Now, all these bounds are really forever. It's not just.
Oh, you asked how long? Oh, I guess he asked the question, not just you first time reach equilibrium and then you get crazy again, but do you stay there? Because that's what equilibrium means. It's not just you reach it, but you stay there, right? That is difficult to be a star. I mean, everybody is a star for 15 minutes, but to be a star for 40 years, that is difficult, right? So what about equilibrium? Now, here is another dramatic result, and I put it in this kind of PBS commercial format because that's what everybody understands, including me, that let's go to the good case. So the Maxwellian. And let's see the family of all nice sets. Then the situation is this, that the system reaches square root equilibrium for a typical Maxwellian velocity distribution, whatever the starting point configuration was picked by my enemy, after a few zigzags, 4, 5. And then it stays there with respect to this family. Okay, now I actually computed it with 20. And then what I got, that it stays there for 10 to the 50 years. So let me repeat. And actually for 99 point, and here again I can write, I guess, 59s. So for the this is so shocking that the system not just reaches, okay, 20 times square root n equilibrium in a couple of milliseconds after a couple of zigzags, bounces, but it stays there with respect to all boxes and nice sets, no violator. None of them leave that bound for trillions and trillions of years.
This is like n squared. What is this number? What is the number 10 to the 15?
Yeah,
as a
Oh.
factor of n?
This is e to the 20 squared over 2 Oh, plus. One of them, which is e to the 200. It is a very big number. So I was actually generous. Is it? I guess it is greater than 10 to the 50.
It depends on the constant in front of the square root number.
Now the constant
So
is
what is the 20? I mean, I'm just wondering.
the deviation. Yes.
So then what happens?
So the message is that it behaves, okay, this is the large deviation, the reciprocal of the large deviation probability. For every probabilist, you know what it is. It is the tail probability of the normal distribution. And the message is that the system becomes fully, okay, starting from something extremely off equilibrium, like Big Bang, for a typical Maxwellian velocity distribution, after a few bounces, it becomes so full-blown randomness that we can apply the intuition of probability theory, the large deviation, that the probability that this is violated with this lambda is e to the negative lambda squared over 2. What would be the probability that you flip a coin,
No, okay.
capital and
But that doesn't answer my question. Because once you've picked your random initial conditions,
yeah.
I want to know the time series for when t goes to infinity. What happens? This gets violated and infinitely often? I mean,
Oh, yeah, okay. So, you know, for me, 10 to the 50 years is a kind of the limitation what I care about. So, actually, now, there is a famous theorem, the Kronig-Kervay equidistribution theorem, which tells you what happens if you have infinite time. And that theorem says that if for every particle you pick a velocity such that the velocity coordinates, there are 3 end velocity coordinates, are linearly independent over the rationals, which is the typical case, the generic case, then on infinite, then the system will take all crazy configurations. So it will go back to almost Big Bang. It will go back to anything you want. So let me repeat. But then you don't have a clue about the time. You really need infinite time. Actually, maybe I am the first guy who discovered this fact. Because somehow nobody really studied this damn subject. Actually, I am happy to talk about everywhere, because maybe somebody will come to me, and you know that Hinch improved it in 1945, and I don't know, and everybody knows it in, I don't know, in Philadelphia, and so and it okay, so here is a surprise. Okay, what is the Kronig-Kervay equidistribution theorem? I need it in extremely high dimension. That is the twist. And also there is a twist that this is a billiard trajectory, and there is a geometric trick to turn it into a torus line. So I just to answer that very good question, I will talk about a little bit about the Kronig-Kervay equidistribution theorem, which is number theory. If you never heard about that, that is a great theorem. Is it a blackboard? Yeah. Okay. Then, so the simplest form is just the two-dimensional form, and it says that if you have a torus line in 2 dimensions, starting from an arbitrary point. So this is a torus line. You know, it jumps, and everybody knows what a torus line is. So this is like a PBS picture. And if the slope is irrational, then the torus line is not just, is uniformly distributed. I guess everybody heard this, the famous theorem. Now, I need it in enormous dimension with capital M particles actually in this, for this 3-dimensional space, because I put all n particles with the 3-dimensional velocities into a super line, I mean into a line in the 3n dimensional space. Now you can ask, wait a minute, that is a zigzag and not a torus line. But here comes the trick, which was discovered 100 years ago, that a billiard trajectory can be converted into a torus line like this, that when it bounces back, then we take the reflection. Then now it goes, and now it goes here, and then I can go up. So the trick is, of course, I don't have room for that, think about it. If you have this 1 by 1 square and the billiard pass, by using this reflection on the sides, it is equivalent to a torus line in the 2 by 2 square. This is a famous trick. It's called unfolding. Unfolding, this is a, you can unfold, I mean, you can convert a zigzag billiard trajectory into a line. Do you know this trick? Do you want to have a better picture or more explanation, or this satisfies you?
We want to see the proof.
Yeah, we want to see.
Oh, what proof? Oh, this proof. But this is not entropy. That's not my subject. Oh, okay, you want to see my proof. Okay, then at least I prove you a key lemma. Okay, the key lemma, now, it is based on Fourier series. And
So this don't have to do with the geometric entropy?
this one, what bounds? These, the 2, I mean the 4 and the 1,000, or what, 100? What bounds?
The weak equilibrium does not.
No, we are not there yet. We are not there yet. You stopped me before I could talk about entropy and want me
Give
to
you another hour.
to give me a proof. Okay, I give you at least something which is this. So what is a mathematical lemma, at least, which emphasizes this enormous difference? So we use Fourier series, and we can write down the discrepancy in terms of the Fourier coefficients. So we take the a test set, and the characteristic or indicator function of the test set, if it's measurable, it has a Fourier series, and we use that. Now then, eventually, when we take average over all initial velocities, that is obviously a crucial step in this proof, because I cannot prove it for every initial velocity, but for the majority. So what happens for some kind of an average? Now here comes a lemma, which is a, do you see if I write here? Then consider this. What corresponds to the first case is the integral of I w dot v. V represents velocity. So in the first case, v is distributed on the unit sphere. This is the, okay, I write sphere because S was unit sphere. And integrate over the unit sphere. So all directions. Now the unit sphere has surface area 4 pi, so I just normalize because everybody normalizes. And this is this. This is sine. We are in discrete space. So W is an arbitrary 3-dimensional vector. Sine, which corresponds to the Fourier series. So that's why I need it. So this is a lemma. If you call it T lemma. Okay. Now this is W magnitude over W magnitude. This is just the Euclidean norm, so the length of the vector. Now this corresponds to the first case, photons. Now what happens in the second case? Can you still see this? Then we integrate over the 3-dimensional space with this distribution. So that is the Maxwellian. So we integrate, V runs over the 3-dimensional space, and e to the I W, of course I is square root of -1 because Fourier series, dot V dV, and now this is I have to divide by 2 pi to the 3/2, which means normalization, and then I get e to the negative W squared over 2. Oh, yes. E to the negative V magnitude squared over 2. This is absolutely crucial. Sorry about that. This is the density. This is what I wrote down. Okay, so this is the perfect analog of the first, but instead of constant speed, we have the Maxwellian speed distribution. Now, what is the dramatic difference between the two? The asymptotic behavior of the right sides as W tends to infinity. This tends to 0 super exponentially fast. The sign is basically 1. I mean, it's plus minus. So if W tends to infinity, then it is like 1 over W, which is just a linear, I mean, that is slow. So this tends to 0 much faster than that if W tends to infinity. Now this is just a detail in the middle, but now.
So this is where you said the smoothness of the distribution matters?
Yes. And instead of this, I could use so. Now probably, okay, so the first reaction of mine was that the Maxwellian distribution is probably the reason why it is so unbelievably good and reaches equilibrium so fast, is that for this the coordinates are independent normal random variables. Probably you learn probability theory, and then you learn the 3-dimensional normal, which has this property that V is V1, V2, V3, and then the coordinates are independent, one-dimensional, standard normal random variables. That is the only, that characterizes that is an alternative definition of the 3-dimensional, which is, I am stupid. It is clear from this because this factorizes. I mean, of course, I just proved it. I mean, this is nothing else than e to the negative 1/2 v1 squared, v2 squared, v3 squared. You see? And then this is a product, e to the negative 1/2 v1 squared, e to the negative. So I am doing high school mathematics. Now, this means the variables are separated, which means that they are independent. They represent independent random variables. Now,
But if you took like
but there are infinitely many other speed distributions which don't have this. This is the only one which has this property that the coordinates become independent. But there are infinitely many others which are kind of equally smooth, like the normal distribution. So it is first I saw that this is the one and only one, Paul McCartney, or I don't know, Johann Sebastian Bach. That there is one Johann Sebastian Bach. But no, there are many of them. Actually, infinitely many, which are equally fast. Now, now how to prove them? How to prove this lemma?
But those infinitely many, for them there will be no. Are there examples of distributions that converge fast and have some linear dependence between the three coordinates?
I don't know. I don't know. All what so I thought maybe, as I said, this is the only good one, but there are many others. Now, but this is the simplest looking in the family. Yes?
Can you put it, this is the best one? This one is the best?
No,
Faster?
they are, actually, I don't know whether you can, yeah. I don't know that it is literally the best or not, but I could prove that, okay, so what was the waiting time here? How many bounces? Where is the square root log n? Should be a square root log n somewhere. Oh, here, right? I said this velocity distribution makes even Big Bang into full-blown randomness after square root log n bounces. There is some constant, which is actually small, like 1/10. But, and we need another constant times square root log n. So actually, this is best possible order of magnitude. So I don't know what is the best constant, but the order of magnitude, so you do need square root log n bounces. If n is really, really, really huge, like 2 to the 2 to the 2 to the 2 to the 2, then square root log n is still 2 to the 2 to the 2. And you need that many. Now, that is actually related to the entropy, studying the entropy, which was that we want a delicate, here I was just talking about how long does it take to square root equilibrium. And as I said, the system then stays there for trillion years, at least with 20, and maybe for billion years with 10. So the system stays there, but what happens in the approach to square root equilibrium, and that's what the entropy describes, because it is a slow process here. It is 100 years. And even there, it is an hour in the third case, uniform in the unit balls. So that is an hour. So you want something to increase. So what the heck is that? And Okay, and that study led to this fact that these bounds, square root n, square root log n, fourth root n, are needed. Not just it works with that, but they are needed. Now, so that would be entropy. So do you want me to talk about entropy, or you want me to prove these two lemmas, or
Lemmas, no, but this is then used. I mean, you have to take the convolution with the characteristic
yeah,
vector of the
yeah,
of an
yeah.
arbitrary set.
And add them up.
You have to pick it somehow, right? I mean, you want to pick, like for a lower bound, you need to pick it to say that, or just an average. What sets are missed by? I mean, if you are proving a lower bound that you need at least square root n,
Oh.
is it a worst case, or did you just average?
No, the square root log n is the following. That actually, that is also 50-50. That you pick the Big Bang because you hate me, and my friend picks a nice set, a sphere, and even then, for 99% of the Maxwellian velocity distribution, we have to wait for square root log n bounces. That is the theorem. Now that leads me to the entropy, but well, actually what you did not ask, and I love to talk about it, is what happens if we take more general motions. So what was the motion? The motion what I studied was a billiard trajectory, which with that trick is actually nothing else than a line, constant speed motion on a line, modulo 1. But what about general motions? I mean, an arbitrary parameterized curve describes an arbitrary motion of a particle. So what happens if if we give curves? Like so far, the curve was a line because we all know what a billiard ball does. But what if, now, okay, there are two kind of motivations for studying an arbitrary curve. One motivation is that actually a charged particle in a magnetic field moves on a spiral, on a helix, because the magnetic force is perpendicular. It is a cross product to the velocity. I am teaching calculus 3, vector calculus, so I am very proud of my use of cross product. Non-charged particles, they just move on a line because the magnetic effect doesn't bother them. So here is a far-reaching generalization of this model where it's really very far-reaching. It took me a long time to be brave enough to go that far, is that for every particle has its own curve. So some particles have this, some particles have that, some particles have this. So every particle has its own curve. The first particle, the second particle, the third particle. Now that is a far-reaching generalization. Of course, a physicist would scream at me and say that this is just stupid generalization, what mathematicians do to publish stuff. But I think that is interesting. So how far can you go with this? And it turns out that all what matters is that the curves move away from the start, like a line. Actually, they can move very slowly. Like, now this is what a physicist would immediately interrupt me at the beginning of my talk, because they actually did, is that saying, oh, gas molecules don't move on a line because they collide with, they collide, so they actually move on a random walk, which is kind of a zigzag in the space because of collision. Now then I can say, okay, but I don't care about the motion of a particular particle. What I care about is how many particles are in a test set. And of course I cheat, but it is a standard cheat in any physics model that if two particles bounce, then what if they just switch a trajectory? So this guy moves like, okay, so actually it means it would go back, and that would go this way, and so we lose the identity of the particles, but they stay on the same line. Do you understand what I tried to explain?
Yeah, although in the gas model you have a distribution over the, so the curve is not a curve, but actually a distribution of curves.
Now, what I am saying is if I count the number of particles, but I don't care about who is there, then this is kind of a all right cheating. But if the particles are different kind of particles, then this is an enormous cheating. If they are identical particles, then it is not a big cheating. Different two or three, many, I mean, in a gas we have different kind of particles in the general case. And then a particle really moves like a random walk in the space. Now that moves away from the start very slowly. We know the distance is square root of the time. If we take unit speed, we all know that the distance is square root for the random walk. Now, so I even allow that which moves slowly, but on average it moves with square root of the time speed, for example. So then a trajectory can be kind of a three-dimensional random walk trajectory. For every particle, a trajectory. Now then it is, of course, it is a cheating, but every model is a cheating. What mathematicians can solve, they are all toy models compared to reality. So then what can we save from these statements? And it turns out that this is so general that, roughly speaking, the particles can have arbitrary, every particle can choose its own trajectory, but on average it has to move away from the start. So it has to drift away. For example, square root t speed is fine. Of course, for linear, what we studied so far, it was t. For a random walk, it is square root. But that would just square the number of, for example, if it would be square root, we can guarantee that every particle moves away with at least square root t speed, then the 4 bounces would become 4 squared, 16 bounces, which is an unbelievably good result. That is still like 2% of a second. So there is a far-reaching generalization of this, which says that every particle can choose its own trajectory. all what I require that each one moves away from the start with some given speed, like square root t, in some weak average sense. But let's take the rigid sense. It is always square root t, monotonic, at least square root t. So after time t, your distance, and t is at least 100 seconds, your distance is at least square root t from the start. And I am studying now the unit torus. So it means then I take everything modulo 1. Then the number of bounces, then for a typical, now then what is a typical initial velocity? Here, okay, what was, okay, here we had constant speed in the first case. Here we magnify the speed, that means we magnify the curve. When you magnify a line, you stay on the line. You just go faster on a line. When you to save the proof, I have to magnify the line with some factor. So the speed, this x, is the magnification factor. So if I had this curve, the magnification by 2 is this. So then the statement is this. Every particle chooses its own trajectory. Then for 99% of the Maxwellian velocity distribution, which means, and a trajectory, automatically this gives you, this is a parameterized curve, a speed distribution. So you know the derivative is the speed. So what I mean by that, even for a line, you can go slowly, fast, slowly, fast. There is an arbitrary speed function involved, even for a line. Here, the parameterization of the curve, RT, the derivative is the speed, and it's not constant. It depends on what curve you give. So the speed don't have to be constant for the time evolution of the trajectory. All what I require is that it moves away from the start. Yeah, it smells, the lunch or whatever. And of course, you take it modulo 1 because now we are in the torus. And for almost every velocity, initial velocity choice, which means for the curve, I choose a direction. And I choose a magnification factor. So this becomes that or that. And for that initial choice, after less than 20 bounces, the system is there and stays there for billion years. So there is a far, far, far-reaching generalization. What also shocked me that I can go that far. Now, in 2 dimensions, the rotation simply means an angle. But you know, in the space, it is trickier because if you have a proper 3-dimensional curve like a helix, then its rotation is actually rotation of the 3 space, which is the special orthogonal group, which is not just a direction. You know what I mean. It is a coordinate system, and you rotate the coordinate system. So it's not 2-dimensional like the sphere. It is 3-dimensional. But, okay, it's 3-dimensional. So what? But for a typical Maxwellian distribution, such an unbelievably general time evolution very quickly reaches equilibrium.
Say something here. So 2, yeah, if you add collision, then what you're saying is this will not improve things because this But I want to make the point that one, on the other hand, will improve tremendously because if you have Maxwell,
What you are saying that
Maxwellian
a
distribution
collision
is
would
precisely
speed
the
up.
collision
Oh,
distribution.
sorry for interrupting.
The Maxwellian distribution is precisely the collision distribution. You have the
But
conservation
he
of
was
kinetic
not allowing.
energy.
He was not
No,
allowing.
understand.
That was not the Maxwell gas model. It was a deterministic collision. In the Maxwell
Yeah,
gas
yeah,
model,
yes.
when
That's right.
This is deterministic.
it's
Yeah.
deterministic. But
Yeah.
if you took the Maxwell gas model, which allows whenever you collide,
The Maxwell.
you choose a random direction again.
No, but that's not what you do.
No?
No. You assume they're tiny spheres.
Yeah.
It's totally deterministic.
No, they are points.
What?
They are points.
I know there are points, but to have collisions, you have to assume they're tiny little spheres, otherwise points will never collide. So assume they're tiny little spheres.
I don't talk about collision. I imitate collision with an arbitrary curve which with zigzags, and then I tell the physicist I cannot handle collision. This is the second best thing what I can do. Sorry, I cannot do more. That is what I would tell a physicist.
Yeah, but let me tell you. Let me just finish my point.
Oh,
And,
I am terribly sorry.
I'm just saying that you can add collision, deterministic collision to your model with tiny spheres, and number two remains true.
I have no clue. I don't know.
Yes, it
I-
is obviously true because
Why? Why is it
because
obvious?
square root of log n is optimal. That's what you need to. I mean, it's independent normal distributions. I mean, that's square root of log n has to be optimal.
But that's not your point.
So
then.
no.
No.
So
That is a guess what you are. You have a conjecture.
Let's just
Is it a
let me
conjecture?
finish my point. Just let me finish. It's just one sentence. Then you can talk all you want. So two is like you can add to your beautiful theorems. And by the way, if you have deterministic collision, this is still true. You still have to send down. Number one, on the other hand, if you add deterministic collisions, number one will not be true. In fact, it's certainly false. And that's it. I'm done.
But I would agree with you. Only it's not deterministic collision. When you look at the hardcore model, when they are actually tiny spheres
Yes.
and they collide, the outcome, the way they reflect, is allowed to be spherical,
Yeah.
as random, as long as they maintain the same momentum and So
Yeah.
it's not. If it was just replacing identity, it doesn't matter. Little spheres or points.
That will not
Nothing
work.
will happen.
Yeah,
So
nothing
you
will
have to
happen.
go.
Yeah.
It's random. This is a standard statistical model, but then you add randomness in every collision, which is not good.
Yeah. I just want randomness for the initial condition, and after that it's 100% deterministic.
But
This is what I want. I don't want to insert randomness as the time goes on.
yeah, but physicists do not. The physics itself does not add randomness. When two balls collide, it's a completely deterministic process.
That's
They-
true.
As for them, because they simply assume there's no reason to assume any direction is pure direction. Therefore, we might as well assume it's Maxwellian. But actually, that's not true. I mean, the physics does not work like that. So, in fact, well, I guess I've made my point.
Okay, so here is what I can say about collision. I wish I could prove anything about collision models. I cannot prove anything about collision models. Actually, this is so fast that I think collisions actually slow it down a little bit because this is super exponential. I mean, even blowing up the atomic bomb is exponential. I mean, everything is exponential. Nothing is super exponential. This is my totally amateur high school level physics knowledge. So I think this is too good to be true in reality. This is a mathematical theorem. Super exponential doesn't exist in nature. That's my wired guess. So actually collision slows it down a little bit to exponential because in reality everything fast is exponential, I think. But I don't know. I am just a pure mathematician. And again, I wish I could prove something about collisions, but I cannot. So this is the best how I can imitate it, that I let the trajectories be deterministic curves which imitate a random walk, how actually a concrete particle moves due to the collisions, particle-particle collisions, but beyond that I cannot prove anything. So
Okay,
this is the sad truth.
You will not be angry at me after you already arranged me as your enemy. You want to tell us about entropy?
Okay, so then let's talk about entropy. Now, so now you understand that entropy is to go there. Now, well, I didn't talk about strong equilibrium yet. So, okay, next time, if you invite me second time, then I talk about strong entropy. So actually, this is my favorite, but okay, I talk about geometric entropy.
You chosen to talk about.
Yeah. I tried. I was kidding. Now, so entropy. Now, what I want is simply a point set and for a point set to define entropy. Now, physicists don't define entropy for a point set because a point set, any point set is like another point set. They are equally likely. So what does it mean that what the heck increases? Now, of course, what I study is a motion, a typical motion.
The microphone fell.
Oh, I'm sorry.
Nobody will hear you.
So what should I do with this? Oh, okay. Oh, that's it. You are right. Wow. I might swallow it. So we have endpoints in the unit square where I can make a picture. Actually, it can be. Maybe I have the unit. Okay. So here is a point set. What is the entropy? Now, it sounds like completely stupid question, but I want something which increases. So what I have in my mind is that the particles have a typical motion. So this is that I freeze the time. And so what happens to the system when the particles have a typical motion? Then what you expect is that the uniformity of the system increases. That is a totally natural, common sense conjecture. Now, what do physicists tell you about entropy? There are two properties which define entropy for them. One is that this is additive in equilibrium. Okay, thermodynamic equilibrium. I will talk about that. The second is that what we have in Boltzmann's gravestone, tombstone, I don't know how it is called, then there is a formula which says that entropy is some constant logarithm of the number of microstates which correspond to the given macro state. Now, this is typical physicist talk. I am not going to precisely define what they mean, but W is the number of relevant microstates of the system. Now, this is what you find in the physics books, this sentence. And this is on Boltzmann's tombstone. Okay, so how does this and increasing uniformity are connected? So then I said, well, the most trivial start, which doesn't work, but let's pretend. We have to start somehow. Is to have a test set S, and to see whether for a typical system is it always true. Oh, and of course, it increases as the time goes by, as time increases. Now, is it true that if I pick a test set, then the time evolution makes it more uniform? Now, there is a trivial counterexample, even in one dimension, that now suppose that this is actually the torus. So when you leave, you come back at the other end. So this is a closed surface, if you like. So everything is modulo 1. And suppose that you have, this is your test set, the first half of the unit interval. This is your test set. And suppose that here you have a lot of points very close to the boundary, and here you have n half, and there you have n half. So I am just giving you a high school level counterexample. Example where the typical time evolution makes it worse, at least temporarily. Because what happens if the particles have a typical motion, then you can see that because it is almost at the end of this test set, half will leave, half will get inside. So at the beginning, it was perfectly uniform because this is a half of the set and half of the points are there. But if you wait just a little bit of time, half will get out, and you will have only n over 4 points, and these guys didn't have time to go there, because if they go this way, then it takes time, and if you go that way and jump, it takes time. So for the time until these guys reach the test set, we have n over 4 points instead of n half. So that is an enormous discrepancy. So it means for a quite a long time, the system became less uniform with respect to this test set. And
to be fair, the second law refers to a closed system, and here they're trying to apply it to which is not a closed system.
What is a closed system?
No, it's not.
This is a closed, this is a torus.
No, S is not.
No, S should not be closed.
Just let me.
Oh, sorry.
Yeah. I see your point, but it's not being fair to the second law. The second law applies to a closed system. Now you're try to apply the second law to S, but you cannot do that. You have to apply the second law to the entire cube, because it's meaningless to apply the second law just to S.
I am
So
just doing mathematics. I don't do physics. These are just motivations,
But
vague motivations.
No, but 3 applies to the entire box. You have to say within the entire box.
Okay, I will return to that. Okay, but suppose, okay, I understand your criticism, and
I'm your friend, remember. Just imagine what Evie would say.
yeah, but I can disagree with my friend. This is a friendly disagreement. And now, you are absolutely right, but also I am right that I don't have a definition yet. So instead of giving you the damn definition, I try to show how I came to that definition. And here is a trivial example which shows that one test set certainly doesn't work. So then we need a family of test sets. Now, because this is the torus, it is translation invariant, so it is very natural to guess that instead of S, we take all translated copies. So this runs over the unit. Actually, it works in any dimension, but I just picked the two-dimensional case for simplicity.
You average over translations.
What?
You average over translations. For every set, you average over the
No, actually, what I do, I simply take the square integral of the error. So I take, okay, this is a point set. God. What is a point set? Y. Y1, Yn. These are points, given points. And kind of the analog of this is that I take an arbitrary shifted copy of the test set, translated copy, and I count the number of points in it, y, and compare it to n times the area. Now, it works in any dimension, but let it be the area. And I square it. And integrate over all translations. Now, let me call it like delta, because square integral, this is kind of a average square discrepancy. That's why I put the square. Delta is kind of discrepancy error, and depends on S. And the given point set, Y. Now, so how about this? Now, what does it mean that I take the time evolution? So those little arrows indicate that I study some motion. So instead of y, I want to study this for some yt. Okay, this corresponds to the case when the time is 0, and here t is positive. And so what it means, a typical time evolution of that point set, what does it mean? I will return to that. And maybe there is an increase in this. So maybe we are so lucky that whatever initial point configuration we started with, Big Bang or whatever, my enemy picked, and whatever test set also my enemy picked, maybe it is true that for a typical time evolution by some typical motion, this will always increase. Now, by the way, this is linear. Okay, this quantity trivially satisfies what we say additive in thermodynamic equilibrium, because equilibrium means randomness, and if it's a random n set, then this is a variance. And the variance is linear, which is additive. So what it means, if I have a random n set and a random k set, and I put them together, I get a random independently, that I get a random n plus k set, and this will show n plus k, because this is the variance for a random n set. So that part is okay. So maybe it works. So maybe it is that simple, that we just have to take this average, and that will show some increasing. Now, actually, I am dumb. because this obviously decreases. So if we take the negative, that will increase. Do you understand? Because now, actually, this is a little bit more complicated. So the situation is this, that let's start from bad point distributions, like Big Bang, which are far from uniformity. In that case, at the beginning, when time is 0, so it is like very non-uniform, then this will be very large. It can be as large as n squared. For example, for Big Bang, it is the order of n squared. Now, randomness means n. So it will go down from n squared to n. Now, actually, it can be much smaller. We have an expert in discrepancy theory, and we all know that there are some point distributions, for example, some kind of a tilted lattice, which is so uniform, and if S is some rectangle, then a kind of a tilted lattice, like square root 2 or something like is the slope, then this can be log power. So it can be as small as logarithmic or so it can be much smaller. But what will happen with a typical time evolution, even in the slowest case, which was the number 1, the case of the photon, the constant speed, when it took 100 years to reach square root equilibrium, after a couple of zigzags, it goes up to there. So when you are below n, it is a possibility, then even with the slowest time evolution, after a couple of zigzags, which is a couple of milliseconds, the system is already up there. So I kind of ignore that, which is unfair. But what I say, we just wait a few milliseconds and start to study the time evolution after that. And after that, it will stay there. So the really interesting case is what happens if it's like n squared or n to the 1.5 or something like that, which is a very non-uniform point distribution. What happens to the time evolution? Is it really true that this goes down in a monotonic fashion? So then I can call its negative an entropy. So this is and this actually goes up. So this is what I call entropy. Actually, this is a relative entropy because it depends on this test set. So I call it S entropy. This is the test set. So is it really true that the S entropy always increases? Now, in what sense? Of course, we just study the typical time evolution, typical velocity distribution. Now, okay, we can just have the most narrow system where the particles are billiard balls, and we have either the constant speed distribution or the Maxwellian velocity distribution or uniform in the unit ball or whatever speed, isotropic, so every direction is the same, but you pick your own favorite speed distribution. Is it true that for all of them we have a monotonicity here? And, and the statement is that in some sense, yes, under these, and actually even much more general, we can pick, instead of the lines, which is like a billiard ball, an arbitrary curve, but just one curve. So it is like every particle has the same trajectory because they are identical. You can pick this one, doesn't matter. So they have the same trajectory, but for each particle you choose the initial direction, and you choose the magnification factor for Maxwellian, but you don't choose just let it go in the constant speed case, so it depends on what velocity distribution you choose. And the question is, can we really say that this is a monotone increasing function?
So
Is it monotone increasing for 99.99% of the initial velocity?
And for every s?
Yes, for every s, for every y, and for every trajectory, but just one. So there is no plural here. We just pick a trajectory. And then the answer is this. In some sense, yes, there is such a shockingly general theorem with the following. I mean, precisely it is like this. This equals kind of the equilibrium part, which is because of the negative. Okay, you know what? I don't like negatives. That confuses me. So I just pick negative to satisfy physicists who say that it increases. But it equally satisfies me if it decreases. So, and I hate negatives. So I want strictly decreasing as time goes by. And the answer is yes, in the following sense. This can be written as n plus a decreasing. So kind of a function of time, which is decreasing. So what does it mean? We have, and it can be expressed in terms of there is an explicit formula depending on which, and every velocity. Now, stupid me, no, even if we have a trajectory like this, then of course I have to decide whether it's number 1, number 2, or number 3, or number 4, or your favorite speed distribution. So now for every, now actually this is a little bit, okay. So I am a mathematician, so I am supposed to give a correct statement. So let's start with the Maxwellian. Now this will prove actually why that square root log n bounces are needed. So we have the Maxwellian velocity distribution. So we pick a trajectory, we pick an arbitrary test set, an arbitrary initial n-element point set, and then we study a typical Maxwellian initial velocity distribution, which means for every particle I choose a direction and the possible magnification factor according to their density function. Then we study, then we can write it down. And what does it do? for this, we have an explicit function which has a constant term, which will be the limit if t is large. That corresponds to total randomness, full-blown randomness. And there is a part which is strictly decreasing, literally decreasing. So what does it mean? It means that, now this is only for 99.9% of the initial velocity distribution. So we cannot say, and of course, in general, we cannot guarantee this for all of them, because this, when it is a, when the same bunch moves from left to right, then no increase or no decrease. But this does, and this describes the typical behavior, which goes down with square root log n time from n squared to n if you start, for example, from Big Bang. So this is a totally explicit function here, which is literally goes down like crazy. So this is a very general theorem for every initial point set, for every test set, for every trajectory which still has a tendency of drifting away from start. You are in the unit torus. For 99% of the Maxwellian initial velocities, you study the time evolution of the system and this function here, which is an average square discrepancy. And it has this has an explicit formula expressed in terms of the Fourier coefficients of the characteristic function of S, which has the constant part and the dynamic part, and the dynamic part literally decreases. It is a monotone decreasing function which goes down like crazy, very fast for the Maxwellian. Now, what happens when the Maxwellian is replaced with the case of photons? So the new case, when we have constant speed. Then again, we have an explicit function, but that explicit function is not literally monotonic, but it is explicit. It is like this. So it has a tendency of going down. But it is a clear tendency. It's not monotonic for this. And for the third one, the same picture. I mean, it is a different, and this explicit formula shows why it is square root n bounces what you need. So this is actually a very slow, relatively slow going down. The other one is a faster. In the third case, when we have the uniform in the unit ball, it is faster. So here it's square root n bounces. It is fourth root of n bounces. And here we have square root log n bounces. So these explicit formulas tell you what happens. And the shocking part is that this is so general. Okay, now this is, okay. Now how to prove it? Now to prove it, I oversimplified this equation. Okay, sorry. Yeah, this is monotone decreasing, and plus there is a plus minus n fluctuation. No, sorry, this is ft. It is like a square root ft fluctuation. So what does it mean? This is large for, this is like n squared. So that is immediately becomes negligible because it is in the range of the limit. So it is like, you know, it is n squared. So this is there is a negligible part. So, I mean, even this is monotonic. And that makes even here kind of, I don't know exactly, but this is totally negligible. Now, of course, to really understand this, I should write the explicit formulas for at least the 3 cases and to study what this means. But trust me, this is what we have. We have a main term, which is a monotone decreasing function. And this is far the main term when we are far from equilibrium. This strictly decreases. There is a fluctuation because what I study, I study the average of this and the average of the variance of this. And the variance is, so I use kind of totally routine ideas. Second moment method, what I use, nothing else. The simplest technique of probability theory. And that's why we have a fluctuation, because when you use Chebyshev inequality, there is a fluctuation. I mean, an error term. But the punchline is that the fluctuation is negligible compared to the main term, and so that's why I cannot say it is 100% monotone decreasing, but it's practically monotone decreasing. Now, actually, it is even more. Yeah, this is fine. Yeah. So, so this is what I call the S entropy. It's negative to satisfy physicists. What I also wanted to explain, but I don't have time, why this actually satisfies this intuition. This definition actually satisfies that intuition, because I really kind of wanted to convince a skeptic physicist that this is what that requirement means. That applies in this case. And now here comes the final word, that, okay, this is just a relative entropy, because it makes a huge difference that you choose a very complicated test set or you choose a nice test set. Now, what I consider the geometric entropy is when S is all balls. Well, it is a ball. Okay, actually, all balls. So that is another average. That means an integration with respect to the radius. Radius goes from, I don't know, 1/10 to in an interval, 2/10. I don't care. But it turns out that whatever we get for this, it is the same for all rotated boxes. So there is kind of a universality of, this is kind of a universal entropy. If we take all balls, or all rotated boxes, or all tetrahedrons, we get the same quantity. So that shows some kind of a universality, and that's why That's what I consider the entropy, because these concepts heavily depend on S. And when S is a very complicated set, then what it gives is very misleading, can be very misleading, and there are theorems describing those kind of paradoxes. But this is what we consider natural test sets. And what is good about this concept, that it basically doesn't matter that you start out with spheres, or you start out with cubes, rotated cubes, or rotated boxes, or rotated tetrahedrons. For all of them, you get the same entropy apart from an absolute constant. Now, of course, my time is up, and I am sorry that it took so long, and I'm sorry for always interrupting my best friend, but that's my nature. Sorry. Thank you very much.
Questions?
I have another question. Your square root of log n, does that work in one dimension also?
It works in any dimension, I guess.
But the square root of n should not work in one dimension, right? Because if the speed is the same, then they're all being translated, and so you never mix, no?
They never mix.
You never mix, so you never get square root of n.
Direction is one.
Oh, there is no, okay.
One dimension. There is no direction.
There is no direction. So actually, I just studied 2 and 3. Sorry, I have no clue what happens in one dimension.
No, because from your proof, well, the proof you didn't give, but this thing,
This is true in every dimension. But of course, this is pretty. In 3 dimension, it is much more complicated. It is more complicated in 2 dimension and 4 dimension, but the order of magnitude is similar. So I just use totally standard tools, Fourier analysis, nothing fancy, not Lie groups, no, okay, standard stuff. And here, basic probability theory, nothing fancy. And that's why I am surprised that why people didn't do this before. Okay, so, okay, that's it.
So how is it related? I mean, the scale seems completely different. I mean, Boltzmann's, this log doesn't appear for you. It's something, it looks like a different scale.
It does. Let me tell you how it does, just in one sentence. This is how I justify that this is a logarithm. That if this is lambda squared times the variance, then for a random set, the probability is e to the negative lambda squared over 2, right? So suppose lambda is at least 1 or 100 or 5, then for a random set to has, without square, this is a lambda times lambda times the standard deviation. The probability is this. So what I am saying is I don't know what microstates are, because here there are no microstates, but I can say that this is the probability. I replace the number of relevant microstates with the probability. So this is the probability, and I take the logarithm. And if I take the logarithm, then I get negative lambda squared. And that's what it is. So I'm sure a physicist would scream and say that this is the micro. Okay, how can you define number of microstates for in the continuous case? I just said the probability.
But it's goes? I mean, the range for your entropy goes between n squared and n.
That's right.
And this and the normal entropy, this log would go between, I don't know, 0
Yes, so actually my entropy with the negative is different. It goes from negative n squared to negative n. This is where it goes. And when it reaches negative n, then it fluctuates around there. And that's what equilibrium means. So, yeah, so it is not dead, but it is increasing, and it reflects equilibrium. And it tells you the necessary time to reach that. So, it is good. Of course, it is not the same. So this is geometric entropy. It's not what physicists do. This is what a geometer combinatorics does.